Hello everyone, my name is Leibny Paola Garcia Perera. I am very glad to be here with you today at this CHiME workshop. I will be presenting diarization, the missing link in speech technologies. And first, I would like to thank the organizers. Moreover, I would like to thank my colleagues and students at JHU, the JSAL workshop team, and lastly, the AHU teams that participated in CHiME 5 and CHiME 6. So let's start. Let me share my screen. So here we go. Diarization, the missing link in speech technologies. So what data do we have out there? We have plenty of smart devices, smartphones, recorders, social media, tablets, microphones. And from all of them, we can gather lots of information. But this information is sometimes useless if we cannot have a good labeling of it. So diarization is a way to label these recordings. So what is diarization exactly? So diarization answers the question, who spoke when? Here we have a brief summary of what is diarization and how it is performed. So first we have a speech signal, and then we want to get rid of the silences with a voice activity detection. Then we can do what is called the speaker type classification. That means we can give a tag of a specific speaker type. In this case, for example, we can distinguish between kid and adult, and between real speech and speech coming from devices. Furthermore, we can do what is called speaker diarization. That means assigning a label to each of the speech segments. For example, in green we have the speaker 1, in blue we have the speaker 2 happening at 2 different times. And then we also have speaker 3. So let's say that we have a good diarization. What for? The first scenario that we can think about is for transcribing a meeting. So in here, we can see the transcription of only 3 speakers. So let's say that you record a complete meeting, and then you don't want to take notes, but you want to take a look of what was said by every member in the meeting. So you can use that, you can use diarization to do that. Another interesting application is for transcribing patient-doctor scenario. There is a great demand on this task. The main goal is to extract the patient's speech so that the doctors can monitor the evolution of the diseases. Another goal is to select the doctor's speech from the recording and obtain relevant information, for example, of prescriptions or simply for quality of service. Another interesting goal is how to deal with very long recordings of, let's say, more than 5 hours per day. This one is a very complex scenario. And as an example, I can talk about this nice study that relies on diarization. The Leibny Consortium and members from the Darko community, for years they have been studying how children acquire language and the brain development. This study relates the connectivity between 2 parts of the brain. So they relate the connectivity between the Broca's area and the Wernicke's area. The experiment suggests that the more real interactions, that means the more that the kid receives speech, the more connectivity of the brain and the better development. So for this one, we need a good diarization system that can accurately tag the speakers along very long recordings. Another scenario could be just for fun, as in this picture. It is very similar to CHiME 6. which is very difficult because everybody is not only smiling, as in this picture, but talking at the same time, and there are different things happening. These recordings are also full of noise that, that competitive systems must deal with. So we have seen that diarization is important. So let's go to the story of diarization. But first, what was first, ASR or diarization? In the beginning, the diarization used information from ASR. So we took the timestamps of the force alignment, and then we use it as a BAD and then perform diarization. Nowadays, we usually do diarization and then perform ASR. And from now, I will like to express my apologies from beginning, since I'm gonna talk about a single microphone mainly. This is the story of diarization. This is the state-of-the-art pipeline, and you can see here the speech signal. Then we apply a voice activity detection. That means we get rid of the silences. Then we have an embedding extractor. So this is a mathematical representation of the speech, or in this case of the speaker. Then we have the scoring, so that we compare all these embeddings and get a score out of them. So we compare all versus all. Then with this scoring, we do what is called the clustering, so that this scores gather together, and the scores that belong to the same speaker remain together. And from there, we can get what is called the RTTM. That is just a list that contains the speakers and its timestamps. If we want to get fancy, we can do what is called the resegmentation. That is only a refinement of the boundaries of the speaker in the RTTM. In the end, we will have something like this, some tags that tell us where the speaker begins and the speaker ends. But how to know if a diarization system is good or not? We establish a metric. The most common metric is a diarization error rate. It is composed of summing up false alarm, misdetection, and speaker confusion divided by the total time of the recording. The false alarm is the duration of the non-speech mistakenly classified as speech. The misdetection is the duration of the speech incorrectly classified as non-speech, and the confusion is the duration of the speakers classified as another speaker. With this in mind, we can continue explaining the story about diarization. So the first stage is the voice activity detector, which removes the non-speech parts from the signal, usually silences. The most popular BAD for clean conditions is the energy BAD, which is simple, as you can see, but it works. The main idea is to measure the energy of the signal and tag it as a speech if it's above a defined or estimated threshold. The idea of BAD is shared not only in the diarization domain, but it also works on speaker ID. Now that we have removed the silences, the next thing is to obtain good embeddings. In this case, there are two flavors, I vectors and X vectors. Both of them are mathematical representations of every segment after the BAD. The I vectors, as you may know, come from statistical Bayesian theory, which says that the mean of the supervector of an utterance is decomposed into a universal mean plus a total variability matrix or loading matrix times the factor vector, in this case, the I vector. On the other hand, the X vector uses a DNN to compute the representation. The complete DNN objective is to compute the probability of the speaker given an input sequence. In a first stage, what we have is a process of the data at the frame level and its context, followed by the pooling layer that is usually a mean and a standard deviation. And that converts the previous output into segment level embeddings. From the segment level layers, except the last one that is a softmax, we can extract the embeddings. Then we can jump to the scoring. The most popular method is the probabilistic discriminant analysis. This is a probabilistic version of LDA. It combines intersection variability and scoring all together. The idea of PLDA is that an embedding J that belongs to a class I is written as the sum of several terms, an independent mean, an independent speaker mean, a low rank B multiplied by YI, and a noisy term epsilon. Here we have several hidden variables and an epsilon. In the drawing, we have 4 speakers. These are the means of the speakers. The distance from each point to the speaker is epsilon. B defines the vector space where the speaker means live, and Y are the coordinates of W in the space defined by B. In practice, what we really do is to compute the log likelihood ratio, which ends up to be a quadratic equation where we have terms that depend on the inner product of W1 and W2. So we are just testing if 2 recordings are come from the same speaker or not. Now that we have the scoring, let's do the clustering. We usually trust agglomerative hierarchical clustering. This is a greedy algorithm that starts with a number of clusters equal to the number of speech segments, and it merges the closest clusters iteratively until a stopping criterion is met. It sounds very simple, but it is what we still use right now. And as I told you before, if we want to get fancy, we can use what is called the variational based hidden Markov model resegmentation. So in the figure, each hidden Markov model state represents a speaker, and the state transitions correspond to speaker turns. The state distributions or emission probabilities are GMMs constrained by a Helmholtz matrix in the same way as I vectors do. You can also notice that each speaker has a probability P loop by which the HMM ends up back in the same state. With this approach, we can estimate better boundaries. So now the question is if the derization really works. We are talking about a collaborative scenario with collaborative speakers similar to the ones in meeting. So the answer is yes. But what happens if we have a scenario similar to CHiME 6, where we have a party? The answer is no. So I will also like to show you some of the results that the JHU team got for the Die Hard 1. And here we can see an example of how difficult is the derization. So we can see here the derization error rates for different subcorpuses that formed part of Die Hard 1. So you can see the liver box and the YP, they just contain one speaker, but then the complexity starts increasing up to when they get to VAST and seedlings. So VAST contains YouTube videos and seedlings contains children's speech. So as you can see, it can get very, very difficult in these 2 real scenarios. We have some shortcuts from JSON. But first of all, what are the characteristics of your data? Is it like this one?
But other users who are new to this device need something like that. They need to understand how to change channels and change the volume, so it's easier for them.
Could I see the scroll bar as a sort of shortcut?
This one is a meeting scenario. It's an example from AMI. Or is it like this one?
Just leave it on there.
It'll melt.
It'll melt. Where'd you get it from?
Okay, well, I'll start boiling the water first then.
Preference for the was there final again?
Yeah, here. Where is it?
Oh, there it is. I haven't.
This is an extraction of CHiME 5.
Well, you're up.
Mm-hmm.
Come here. Figured it's 20-minute class.
Water. Lots of water. Your bottom should feel better. It's all clean.
And this one belongs to baby train or children's speech. So as you can see, the first one is easier than the last two. So what are the shortcuts from JSON? So these ones are the shortcuts from the workshop. The orange boxes represent the ideas that we explore and that gave a little bit of improvement. So we have here the enhancement, a better BAD. We have two enhancements, the enhancement in the signal to signal domain, the enhancement in the embeddings, and the resegmentation and the overlap. So let's take a look at each one of them. Let's start with the enhancement, going from the signal to signal. So first we built an SNR progressive multi-target learning based speech enhancement model. The progressive multi-target network is divided into stacking blocks with one LSTM layer and one fully connected layer via multi-learning per block. The fully connected layer in every block is designed to learn intermediate speech targets with a higher SNR than the ones that were computed previously. A series of progressive ratio masks are concatenated with the progressive enhanced low power spectral features together as learning targets. And at test time, we directly feed the enhanced audios processed by our enhancement and directly to the backend system. So let's see if this one works. This is an example of the noisy data.
Lola. Hello. Lola.
And this one is the clean version.
Lola. Hello. Lola.
So you can see that there is quite a difference between the two. Now let's continue with the super BAD. If we have noisy conditions, it is better to have a good BAD. In this case, the most successful approaches were the ones containing an LSTM. And in here we show two approaches. The first one used MFCCs, and then one convolutional layer, and then the LSTM, and then a fully connected layer, and the output is the tags of speech and non-speech. Similarly, we have the SIGNet instead of the future extraction and the convolution layer, and then we have an LSTM, and then the fully connected layer with the same output speech and non-speech. So assigning the LSTM really worked for us. Before continue, I want to make a stop and talk a little bit about the embeddings. It is very true that the better the embeddings we have, the better performance as shown in the table. So we have three cases here. We have the extended TDNN. We have the extended TDNN with augmentation, and we have the extended the factor TDNN with augmentation. So the first experiment was with half the data set of VoxLF for training. The second one uses VoxLF times 3 because of the augmentation. And the third one uses the factor TDNN plus augmentation. We have replicated the data set 3 times. So as you can see, the factor TDNN gave the best results for baby train and AMI, but it was unclear for CHiME 5. But we decided in any case to use the factor TDNN. Now that we have good embeddings, we will need a way to enhance them. We examine how to train an unsupervised speech enhancement system, which can be used as a front-end processing module to improve the quality of the features before they were passed through the network embedding. The main idea is to use an unsupervised adaptation system based on cycle GAN. So we train a cycle GAN network using log-mill filter banks as input. So in here we have the source signal, and then we have the target signal. This one is the clean one. This can be the out of domain or the dirty one. And during the testing, we process the test data through the same architecture, but entering on this side where we set the target signal. And in the end, we get enhanced acoustic features that can be used to extract X vectors. Although in some cases it was just tested on reverberation, it can show some generality to other conditions. Now that we have enhanced our embeddings, we can continue with the scoring and the clustering using the traditional system. But what we want to emphasize is how to do the overlap assignment. This is the first paper spoiler. So I would like to thank Leibny for his effort at the JSON workshop. And I will encourage you to take a look at the paper that is going to be presented at ICAS. So let's think that we already have the clustering and that we need a way to detect the overlap regions. So this one sounds familiar. It's very similar to the architecture for the SuperBAD. But now it is trained to detect overlap and no overlap. It can also be used to detect the speaker terms. So this one is already known. The only thing is the way we are training it. And it works. And it is the input to the overlap assignment. So in the overlap assignment, we have several stages. We have to remember the BB HMN resegmentation. From the BB, we got a speaker attribution matrix, like the one shown on the top. It is a per frame probability that the frame can come from a given speaker. We ended up with a matrix similar to this one, in which each color represents a speaker. The top row is the one that we usually use, but in this case, we are gonna focus on the second row. We usually discard this matrix, but let's see how we can include it here. So let's say that we have the output of the overlap detection and then the second row from our BB resegmentation. We also have the output of our BAD. So that means that we were discarding the silence regions. And what we are gonna do is to intersect between the overlap and the second most likely speaker, resulting in a secondary track in the final hypothesis. Although this idea might be very simple, the result shows that this assignation improves the performance. Now, let's talk a little bit about the data sets that we used. So we used AMI, CHiME5, and BabyTrain. AMI, you know that it is a meeting domain, and it was recording on meeting rooms. CHiME5, it is an indoor scenario, and it was recorded in the kitchen, dining, and living room. And BabyTrain is totally wild, and the setting is uncontrolled. It can be indoor or outdoor. So as you can see, it goes from the easier to the most difficult one. And here we go. What improvements we got in the end? So for AMI, we got a baseline of 49.25%. If we apply a good BAD, we get an improvement, and then a little bit more if we apply the enhancement. If we do the variational based resegmentation, there is another bit of improvement. But what really makes the trick is to perform the overlap assignment. What happens in CHiME5? In CHiME5, we have a baseline of 69.22. We applied an end-to-end BAD that degraded our results a little bit. Then the enhancement improved them. And then we applied the variational base that also degraded our results a little bit. But then once again, the overlap assignment made the trick. And finally, BabyTrain. BabyTrain started with a very high diarization error rate of 85.38. And then by using only the end-to-end BAD, we really improved the system a little bit more with the enhancement, 1 point for the variational based resegmentation, and a little bit more with the overlap assignment. So everything seems very fine here. Can we use this diarization in other scenarios? So this is a side effect of the diarization and speaker tracking. So let's say that you are tracking John along this recording, and you can use brute force. That means compare John's embedding with the embeddings from the signal. And you can continue comparing forever, or you can do diarization. So that means you diarize first the speech, and then you compare it with John's embedding. The results show that it is better to do diarization first and then the tracking. These results, for example, suggest that if you do this windowing, that is this brute force that I was talking about, the results are much higher than when using diarization, even for the ground truth BAD. Now that we have a better idea on diarization, two questions may arise. Are there any end-to-end or neural network diarization systems? And how to use all of this knowledge in a multiple array ASR? Before starting preparing this presentation, I was asking myself, what is the future? But now I'm asking myself, what is the present? One of the first attempts on using the neural networks, I'm going to explain right now. So this is a spoiler. The actual paper will be presented in ICAST 2020. So I really encourage you to look for this paper. It is called Region Proposal Network Based Speaker Diarization, and it was inspired by Region Proposal Network performed on image processing. So the main idea is to find regions of objects and tag them accordingly. For example, in the picture, there are some labels for persons, for dogs, for known monuments, for cars. And the way to do it is as shown in the picture. So we extract some features from the picture using convolutional layers. Those ones are the feature maps that predict the object boundaries. After this, on the left side, the network iteratively selects a bunch of selected regions with redundant information. It also serves as the attention of the network. On the right side, the network computes a region of interest pooling. Both information and the proposals and the region of interest are passed to a classifier, and the output is the picture with all the tagging information. Well, this one sounds very good, but is it possible to use it for diarization? The answer is yes. It is a nice and good contribution so far, and we are moving forward in this direction. So because this one is a spoiler, I will also only tell you that we have the speech signal, we have a neural network process, and somehow we get these region proposals, and these region proposals are the input to some backend, and we can get a very good RTTM. I will encourage you once again to take a look at the paper at ICAST. Another approach is the end-to-end neural diarization. So in here, we have the traditional system, but is it possible to replace this traditional system with only one neural network? The answer is yes, and it seems that it works. So here we have some results given by Yusuke Fujita from Hitachi. So here we have a comparison on the Colholm data set. For example, for the X vector, they got 11.53% diarization error rate, and then by using the self-attention EEN, they got 12.66, and then by using another version called the self-attention EEN adapted, they even improved the performance to 10.76. So these are good news that perhaps will direct a good research direction. And let's see how it works. I can tell you a little bit about the EEN evolution. So the first thing they tried was like a proof of concept. It focuses only on diarizing two speakers. The main idea is to compute frame posteriors from a neural network using a binary cross-entropy loss of frame-wise posteriors with two permutations of reference labels. This way we can minimize the permutation-free loss in here between the output and the reference speaker labels. In a second approach, what they wanted to do is to extend this to multiple speakers. So they used a set of bidirectional LSTMs to obtain the frame posteriors, and they assume that the middle layers of the neural network can extract embeddings. So they establish a training criterion based on the deep clustering loss, so that the clusters are speaker dependent, overlap, or non-speech. The final loss function encourages same speaker clusters to remain in their cluster, or if they belong, if they are different speakers, to really separate to different clusters. This approach, as I mentioned, can work for multiple speakers. And the last approach, and probably the most promising one, is to use some kind of transformer. So we know that the directional LSTMs depend on the past, the future hidden state, and the current feature. So this one is replaced by attention that depends on all the input frames. This encoder, as I told you, is similar to the transformer. It computes and all versus all frame similarity matrix. And the encoder is similar to the transformer with the only difference that it does not have a positional encoding. These three ways of addressing the problem give very good results and encourage research directions. The next one that I want to discuss is the recurrent selective attention network. So this last approach tackles the problem using the knowledge of source separation. So in here, we have a neural network that takes care of everything. It is able to separate any number of speakers and mixtures in a recursive way. So we start with a residual mask or attention mask and a spectrogram. The network pays attention to all the region, outputs a first mask that corresponds to the first source. Then it passes to the second iteration and pays more attention to the shaded areas. The same method computes a second mask that corresponds to the source 2. In a third iteration, the process is exactly the same, and then it stops until the residual mask is empty. So is this gonna be useful for speaker diarization? The answer is yes. And this is another spoiler, so you can take a look at the paper at ICASP. I will explain it very briefly in here. So this procedure, of course, can be extended for different time steps, as is the case in diarization, where we have multiple speakers talking at different times. Although the idea is the same as the one mentioned before, the method first splits the spectrum into consecutive blocks and includes a speaker embedding that is passed to the next block and guides the extraction of the mask of the same speaker. If the speaker does not appear, which is the case in here, at this given time step, the mask is set to 0 and the process continues until we have the residual mask again going to empty. The diarization error on simulated data is quite encouraging. This is simulated data on a meeting scenario. So they started with a 44.39 and their approach went to 33.7, which is quite nice. And now that we have addressed the novel techniques, how can we use all of this in a multiple array scenario? And furthermore, moreover, how can we use this in ASR? So these ones are good news. You can include diarization as part of your ASR. The ASR and the microphones usually have this pipeline. So you have the WP, the beamforming, the GSS, and from there, what you really have here is the ASR, the acoustic model and the language model. This one is the pipeline for the multiple microphone ASR. So is there a space here for the diarization? The answer is yes. You can put the diarization probably after the beamforming, and it will give you the information of the speakers that perhaps can fit the GSS, and you can get improvements. There are two flavors that you can use. For example, you can use the traditional way to do diarization, or you can include some modules that are adapted to your system, or you can use the novel neural network-based diarization approaches. So this is the end of the technical explanation, and now we're gonna see the takeaways from the diarization side. There are some modules that you really need to have in the diarization system so that it can be competitive. So you need a good enhancement, you need a good PAD, you need good embeddings, and you need a way to really do overlap detector and assignment. The new approaches are also becoming very good, and this is also very, very, very encouraging. So these ones are good news. For future work, there are some things that need to be addressed. There is still no a real way to know how to correctly estimate the number of speakers. The second one is that we need newer BADs that can be able to handle the domain mismatch. We need to rethink the clustering. We are trusting agglomerative hierarchical clustering so far, and perhaps we need a way to take the overlap into account. The overlap detection and assignment need further follow-up. And two last questions. How to do effective diarization on very long recordings? It is not an easy task. And finally, a question for all of us. Is it possible to train an ASR and a diarization system jointly? Perhaps we can give a solution to this last question shortly. And that's all from my side. Thank you very much for your time. And if you have any questions, let me know.